Dear students, after studying this module, you shall be able to understand the types of selectivity. Explain chemoselectivity in retroanalysis. Understand the stereoselectivity in retroanalysis and design the synthesis of chiral and achiral molecules. The plants, animals or microorganisms produce a number of chiral and achiral complicated structures. Some of the groups of compounds include antibiotics, alkaloids, chlorophyll, steroids, biopolymers, carbohydrates, fats, vitamins, dyes, etc. The chemist determines the structure of these compounds and try to synthesize them using the disconnection approaches. The synthesis of these compounds become important due to their wide applications. Synthesis from simple starting materials with the predictable regioselectivity and stereochemistry requires the utility of retrosynthetic analysis. There are three types of selectivity possible for any synthesis. Firstly, chemoselectivity is deciding which group reacts. Regioselectivity is where the reaction takes place in that group. Finally, the stereoselectivity is how the group reacts with respect to the stereochemistry of the product. Selectivity can be attained by selecting appropriate starting materials, reagents, solvents, reaction conditions and most importantly protecting and the deprotecting methods. A protecting group or a protective group is entered into a molecule through chemical modifications of a functional group for obtaining the chemoselectivity in a chemical reaction. It plays an important role in the multi-step organic synthesis. Some of the common protecting groups are alcohol protecting groups can be ester, ether, silyl. Amine protecting groups, substituted amines like amide, carbamates, sulfonamides. Carboxylic acid protecting groups can be esters, ester silyl, oxazolene. Functions of protecting groups. Through the protection of these sensitive functional groups, it becomes possible to make the reagents that would otherwise be unstable. Protection allows us to overcome the simple problems of chemoselectivity. The other important functions of protecting groups is to stop a reagent from attacking itself. A more detail about protection and deprotection is given in the module 9. The following sections will discuss the role of stereochemistry in the retrosynthetic analysis. Chemoselectivity. Chemoselectivity plays important role in organic synthesis. This is helpful in those molecules which possess more than one functional group. The selective reactivity of one functional group in presence of the other is controlled by chemoselectivity. The chemoselectivity is supported by protection and deprotection. The following examples will explain the chemoselectivity in the organic reactions. Selective reduction. The selection of a proper reagent plays important role in chemoselectivity. The selective reduction of either the double bond or the carbonyl group in cyclopent 2-enone as represented in the structure is reagent specific. For the chemoselective reduction of a C double bond C bond over the carbonyl, which is C double bond O bond, is performed by the catalytic hydrogenation. Hence, the reaction of cyclopent 2-enone 1 with hydrogen in the presence of palladium gives cyclopentanone, that is the reduction of the double bond would take place. The reduction of C double bond O bond over the C double bond C bond is performed by the reducing agent like sodium borohydride as represented in the figure. The reaction of cyclopent 2-enone with sodium borohydride gives cyclopent 2-enol. In this case, only the carbonyl group is selectively reduced to the hydroxyl group, whereas in the former case, the double bond was selectively reduced to the single bond. Another example of chemoselectivity is the chemoselective reduction of alpha beta unsaturated esters in presence of alkenes. The reduction of the compound 4 with magnesium in presence of methanol reduced the double bond present at the alpha beta position of the alpha beta unsaturated esters, giving the product 5. Regioselectivity. Regioselectivity gives preference for the bond making at a particular place when there is a possibility of the bond formation at the other possible positions also. In other words, there is a preference of one reactive site with respect to the other site. The best example is to explain this is a Markovnikov and anti-Markovnikov addition reactions. The reaction of hydrobromic acid with styrene, which is vinyl benzene as represented by the structure 6, gives 1 bromoethyl benzene through Markovnikov addition. The same reaction, however, if performed in the presence of per acids, undergo anti-Markovnikov addition to give 2 bromoethyl benzene 7. It is to be emphasized here that the regioselectivity of the two reactions give two different products. Therefore, this information of regioselectivity is important for the retrosynthetic analysis, which in turn will lead to the synthesis of the following compounds. Thus, the information of regioselectivity is important for the retrosynthetic analysis. Birch reduction is another important example of regioselectivity. In this reduction method, aromatic rings undergo 1,4 reduction to provide unconjugated cyclohexadienes. This reaction is performed by sodium or lithium metal in liquid ammonia and in the presence of an alcohol. Here, the site of reduction is dependent upon the type of substitution present in the aromatic ring. Without any substitution in the aromatic ring, the reduction of simple benzene, for example in 9, gives cyclohexadiene. Figures show the regioselectivity of the Birch reduction. When the electron donating group and an electron withdrawing group like COOH are attached, the preference is based on the mechanism of the reaction where the radical anion is protonated initially determines the structure of the product. While performing the retrosynthetic analysis, these preferences play important role in the synthetic design of any molecule. As can be seen with the methoxyl group as a substituent and by reduction with sodium in liquid ammonia, the product obtained is 1-methoxy cyclohex 1,4-diene. However, the same reduction being carried out as carboxylic acid as a substituent, the product obtained is cyclohexa 2,5-diene dicarboxylic acid. Stereoselectivity. Stereoselectivity is the preferential formation of one stereoisomer in a chemical reaction. This can be further classified into enantioselective reactions and the diastereoselective reactions. Also, stereospecific reactions and stereoselective reactions. Enantioselective reactions. The stereoselective reactions where the reactant gives enantiomeric products or the enantiomers in unequal amounts are called as the enantioselective reactions. Diastereoselective reactions. The reactions where a reactant gives the diastereomer products or the diastereomers in unequal amounts are called as the diastereoselective reactions. Stereospecific reactions. These are the reactions where the stereochemistry of the starting material determines the stereochemistry of the product and are called as stereospecific reactions. For example, the SN2 reactions, that is bimolecular substitution reactions. Stereoselective reactions. The stereo-specific reactions where one stereoisomer of a product is formed preferentially over the another is known as stereoselective reaction. In stereoselective reaction of an alkene with metachloroperbenzoic acid, the two epoxide formed in different amounts. As can be seen here in the structure, the backside and the front side formation of the two epoxide takes place in different ratios of the products being formed. To summarize, retrosynthetic analysis provides important inputs for the synthesis from simple starting materials with the predictable regioselectivity and stereochemistry. There are three types of selectivity possible for any synthesis: chemoselectivity, regioselectivity and stereoselectivity. Chemoselective refers selective reactivity of one functional group in the preference of the other. The selection of the proper reagent plays important role in the chemoselectivity. Regioselectivity gives preference for bond making at a particular place when there is a possibility of bond formations at the other positions also. Markovnikov and anti-Markovnikov addition reactions are examples of regioselective reactions. Birch reduction is another example of regioselective reaction. Stereoselectivity is the preferential formation of one stereoisomer in a chemical reaction.